Hello, this is Zhao Suojiang, a faculty member in civil engineering at San Francisco State University. Today we're going to talk about the shear diagrams under uniform distributed load. And here we have a simply supported beams under uniform distributed load with 3 kips per foot. And before you can do the shear diagram, first thing you need to do is to draw the free body diagram. As we mentioned in previous videos, what you need to do is to remove those supports and then to expose the force at that support. For a hinge, you're going to have two reactions. One is in horizontal direction, one is in vertical direction. And for those roller on the right, you're going to have only one vertical reactions there. So due to the time, I already draw the free body diagram for us. And now let's take a look at how to find those reactions. We can find those reactions by either the moment at point 8 to find out the reactions at support B, and the moment at B to find out the reaction at 8. That is the typical way we do it. But for this unique structure here, if you look at it, it is symmetrical for both the reactions and the external force. With that said, we can use a simpler method to find the reactions. The way we do it is those two reactions is going to take all those force for the external uniform distributed load, meaning that we have 3 kips per foot for the uniform distributed load. We have the length for 15 feet, and the total load for that is going to be 45 kips. And those loads are going to be supported by AY and BY equally, because we don't have any horizontal force. This AX is going to equal to 0. And with that said, you can find your AY is equal to your BY. That's equal to the total external load by the uniform distributed load, which is equal to 3 kips per foot times the length, which is 15 feet. That is 45 kips divided by 2. That is 22.5 kips. And with that, let's use our typical TDM method to cut the section into pieces and trying to find what is the shear at the different portions. And then we can observe to see if there's any way that we can do it quicker. So here's first what we're going to do is we cut the sections at 1 foot. And on the left hand side, we're going to have this 22.5 kips. And on the right hand side, we're going to have our shear, axial, and moment. And those directions are the positive direction according to our site conventions we taught in the previous videos. To find out the axial load, we can sum the force and the x direction and assuming from left to right is positive. And here what we have is our axial load is equal to 0. If we sum the force at y directions using upward as positive, what we're going to have is this 22.5 minus V minus the force provided by this uniform distributed load, which is 3 kips per foot times 1 foot. That is going to be 3 kips. Is equal to 0. And then we can see our shear is equal to 19.5 kips. And for now, let's just ignore the moment for now, since we're only talking about the shear diagrams. And we can do the same things for cut the sections at 2 feet. Same thing, we're going to have the shear, axial, and moment. And we're going to have this 22.5 kips on the left side. You do the same thing from summation of the x direction force equal to 0, you have your n equal to 0. And if you summed the force at the y direction going upward as positive, then you're going to have this 22.5 minus v minus these 3 kips per foot. Now this time you're going to have 2 feet. Therefore your shear is equal to 16.5 kips. And you can do this for all the sections, and due to time I calculated those for you, and I'm going to list it at here. So here's the shear. The x we have 0.001, 1, 2, 3, 4, 5, 6, 7, 8, all the way to 14.999. And the shear you're going to get is 22.5, 19.5, 16.5, 13.5, etc., and go all the way to negative 22.5, right? And then you can see the trend. We have a decrease of 3 kips for each of the locations. All right, with that, we can draw our shear diagrams here. You can put all those points. If you draw that out, what you're going to see is something like this. This is 22.5, and this is negative 22.5. And for this, what we can observe, right? Observations, so that we don't need to do this tedious process again. The first observation you can see from here is, if you look at the shear, the dropping of the shear is at a rate of 3 kips per foot, meaning the slope of this shear diagrams is equal to negative 3 kips per foot. And that is happen to equal to the negative value of your uniform distributed load. Therefore, the first observation, the slope of your shear diagram is equal to negative value of your uniform distributed load. All right, and if you look at this shear diagram, the shear dropping from point A to point B is equal to, this portion is 22.5 and this portion is 22.5. If you add those up, it's going to be 45 kips, right? That happen to equal to the total load this uniform distributed load contribute. Meaning that the second observation we can find is the shear dropped from left to right is equal to the total load, which is equal to, for this case, 3 kip per foot times the length, which is 15 feet, and that is 45 kips. And those observations are true for all the different other cases. All right, here is our shear diagram under uniform distributed load. I'll see you next time.